you probably own this. This is your Inertial Navigation System. Very complicated to look at, but airliners prefer it over a simple to read GPS even today. It's even in your phone too, a tiny one. This video is about the hidden talent of the INS. And no, this system does not use satellite, radar, radio signals. It's a complete independent system using just physics. But how can that be possible? It's impossible to calculate your way to the long insertion flight route. So what's the insane engineering behind them on why this works? And why does it uphold its 80-year reputation of navigation mastery over the GPS even today? And what's more, why is it paired with GPS today when it supposedly bridges the gap from it? So many questions, but to understand this, we need to go back to the early days to where it all began. The year is 1944, exactly a year before the infamous Hiroshima and Nagasaki bombing. The Nazis created the first supersonic missile with implementation of an early INS was to travel on its own to bomb London. The Nazi inventor, Wernher von Braun, called it the vengeance weapon. Thousands of these missiles launched. It backfired devastatingly. The V-2 was simply too inaccurate. The worst part, the cost was absurd amounts, equal to the Manhattan Project. The Nazis detained the engineer for his defeatist mentality. However, the Americans adopted the idea to breed today's greatest navigation systems in every vehicle. But what made the INS cause these large flight deviations? And what's more, why did the Americans use the INS knowing the massive failure in accuracy and cost? This is because the V-2 had one accelerometer and two gyroscopes, in contrast to the American 6-axis or 9-axis system, producing better accuracy and better performance. More on this later. But the important part is that the Americans found the INS had a talent of not being intercepted by enemies, and it navigated on its own without any outside source. It would be impossible to beat. It navigated plainly from physics calculations. But how does this actually work? And how does the INS use physics to actually serve location to a plane when it can't even see where it's going? Well, each accelerometer or gyroscope is responsible for an axis, measuring acceleration in motion, one parallel and the other angular. However, this still doesn't explain where the plane is. Well, if you heard of derivatives, the position derives to velocity and velocity derives to acceleration. Repeat that backwards, an embedded computer calculates the aircraft position and orientation. Mathematicians call this integration. But this still begs the previous question. If it just shows only where it is, how does it know where to go? Because it's impossible for physics alone to show the flight path to the final destination. Well, in the sea transportation eras, captains would use a magnetic compass to stay on track with the final destination. The same way a flight path from the starting position is accumulated to the present flight. If it's heading correctly to the remaining final coordinate, then the destination ahead is probably clear. The system was revolutionary, until it got way worse. Many reported incidents of the mechanical INS had too many series of major flaws in every major vehicle. It was everywhere, from multiple aviation catastrophes and near-accidental Apollo missions, killing nearly thousands of people's lives because of this one huge flaw. It was called drift. In 1983, the downing of the Korean Flight 007 was the most tragic example of drift. Its intended path was Seoul, South Korea, but due to its continuous tiny tilts in the plate, it headed past USSR, or today known as Russia. And unfortunately, a Russian pilot shot it down for crossing forbidden territory. 269 passengers died in that flight due to this small error. But how does drift happen? And can it be avoided? See, the innermost plate must always be perpendicular to Earth. Let's say the plate tilts upward even by 1 degree. You're dead. Gravity leaks to the forward vector, misinterpreting the plane for accelerating forward, gathering a wrong flight path than the real intended path. Now you may be wondering, didn't they have something that stopped this from happening? They actually did. The INS had 3 gimbal systems. Each gimbal was responsible for each rotational axis. Each had a motor of its own that served a very important purpose in keeping the innermost plate balanced, perpendicular to Earth. But you might find it hard to visualize this. How does this work in real time? I've modeled the whole thing. Let's say the aircraft rolled to the right. The gimbal that proctors the roll axis also rolls the same distance. This roll is detected by the gyroscope and the motor at one end of the gimbal, rotating the gimbal oppositely back to the same distance. This keeps the innermost plate balanced, but unfortunately, this was still not good enough, because small deviations in the plate are always going to occur. This could be from vibrations, gimbal frictions, or mass imbalance. It was simply an impossible feat for perfect alignment. But NASA feared something much greater about the mechanical INS that was a huge problem at that time. This was seen after the explosion of Apollo 13 and the careful monitoring of the first mission to the moon, Apollo 11. It was called gimbal lock. See, if 2 gimbals came into alignment, the INS will lose all sense of direction, and therefore losing direction of the heading pathway. A change had to be made. In the 1980s, they created the strap-down INS, or the strap-down Inertial Navigation System. By strapping the accelerometers and gyroscope, feeds a digitalized algorithmic computer to find the position of the aircraft. It made significant changes, but yet again, not enough to reduce misalignments. The accelerometers and gyroscopes are just too good in detecting every tiny misalignment. Integrating those fake accelerations can make huge deviations in aircraft flight path. If this continues, several more incidents can happen. They needed something that could fix the INS huge deviations. At last, the GPS was released. Pairing up the global positioning system with the strap-down INS corrected its position. However, you might be thinking, why have the INS in the first place when the GPS can navigate the aircraft by itself? Yes, the GPS does provide position precisely more than the strap-down INS, but the dangers of outage are still plausible. The INS is instead a backup navigation tool for short-term routes. What's more, this system cannot be hacked like a GPS, and it's not connected to a network or signal. It's just a plain physics computer, making it still an important factor in aircraft navigation. Thank you for watching, and I hope you enjoy the video.